Dear Prof, this is CSPT Group 3. In this presentation, we'll be sharing our group's work for the LMSYS chatbot arena, human preference prediction, one of the competition on Kaggle. We'll first introduce the competition background, approaches being adopted, data pre-processing methods, features and enhancement, experiments being done, challenges we have encountered, and conclusion. Now let's begin with the background. Large language models are rapidly entering our daily life, but ensuring their responses align with human users is very critical for any successful integration. We will give a dataset of conversation from chatbot arena where different large language models generate answers to user prompts. Our task is to develop an effective machine learning model to make better prediction in order to improve the chatbot future interaction with human users. The provided training dataset contains over 57,000 rows. Each sample comprises a prompt, two model-generated responses, and a ground truth label be A, B, or T. The training dataset is labeled by human judges. Human preference can differ for the same prompt and AI responses. So as a result, model tends to be underfit, with training accuracy hovering around 40 to 60%. Additionally, duplicate prompt with different label and different IDs, reflecting difference in human judgment towards the same prompt. Removing these duplicate values would bias the model towards a single preferred response. Our approach to this problem is building upon existing Kaggle notebook solutions, be it Delta V3 and Gemma 2 9B. This allows us to quickly get up to speed while still engaging with sufficient complex. Experiments were first conducted using the Delta V3 on Kaggle's GPU. It began with Delta V3 because training Gemma 2 9B was not feasible on Kaggle or the Google Colab free version, as both environments lacked sufficient GPU memory to support the models. After testing and confirming that our function and approach were effective in improving training performance, this method was then applied to Gemma 2 setup. We used Google Colab Pro, which provides access to A100 GPUs with higher memory capacity and improved performance as compared to the free version. Since Colab Pro includes only 100 compute units, so our team carefully planned and limit the GPU usage to minimize the competition risk. In the final Gem 2 solution, two separate notebooks were utilized, one for training and modeling, the other for inference. The model used is Gemma 2 9B instructor tune model and Gemma fast tokenizer as the tokenizer. For the low rank adaptation configuration, the first 16 layers were kept frozen and the target module were expanded. Fine-tuning was performed using a combination of original dataset and an additional dataset with the training validation speed ratio of 80 to 20. During the fine-tune in Google Colab, the model learns from the provided dataset and updates its weights. The fine-tuned LORA model then saves the tokenizer as well as the adapter weights. It is then converted into a parameter-efficient fine-tuning model. The PEFT model saves the trained weights, which will be used for inference. These files are then uploaded to the inference notebook in Kaggle, allowing the model to perform prediction offline. This allows us to achieve a public score of 0.94955 on the Kaggle leaderboard, placing us at 762nd out of 1,687 participants, with a ranking in the top of roughly about 45%. For this project, various dataset configurations were experimented with using the Delta V3 model. Results show that adding more data does lead to a higher training accuracy, but it did not necessarily lead to an improvement in the leaderboard score. So the best improvement observed was when training the Delta V3 model on both the original dataset and the additional 33,000 label conversation dataset. For the feature and the enhancements, we first reduced the login frequency of steps from every 10 to every 100 steps, and increased the save interval from every 200 to every 1,000 steps. These changes minimize the interruption caused by the I/O operation. Next, the LoRa dropout parameter was adjusted from 0.05 to 0. This further decreased model runtime. In addition, we also increased the num worker parameter to 12, corresponding to the total number of GPU core available on Google Colab for the A100 GPU. This helps reduce the GPU idle time. Finally, we remove the code in the base notebook model equal to prepare model for k-bits training model and set FP16 from true to false to reduce the startup time. The maximum token length was further enhanced from 1024 to 2048 tokens, covering roughly more than 99th percentile of the total distribution. This resulted in a slight boost in leaderboard score. Furthermore, the inference notebook was configured to only process the first prompt and its corresponding response. This modification led to a significant improvement in public leaderboard outcome. Log loss metric function were kept for both Delta V3 and Gemma 2 model, as log loss assess the confidence of predicted probability and also penalizing the confidence. Monitor model performance and detect potential overfitting during the fine-tune process by computing these metrics on the validation set after each epoch. Several experimentations were also conducted on the Delta V3 model. We began our series of experiments by first testing whether the combination of BIOS-STM and BIOS-GRU layer could improve the model performance. Next, we test each individually. As shown in the figure, BIOS-STM alone demonstrates the greatest improvement. Subsequently, we tried to see whether increasing the number of hidden units could improve the performance. We found that increasing the unit to 256 achieved the best results. Additionally, we came across studies suggesting that TextCN can perform comparably to or better than BIOS-STM. To verify that, we conduct our testing and find that while TXT-CN really improved upon the baseline, it was not able to beat BIOS-STM. So in the end, we test both the fine-tuned Delta V3 and Gemma 2 models. Gemma 2 has outperformed Delta V3 in training accuracy, log loss, and leaderboard score. For the challenge we have encountered is, at first run of the notebook, you will discover that both the training and the inference notebook for the Gemma 2 model had issues related to PIP restoration. In the inference notebook, cargo compensation rule required that internet service to be turned off during submission. As a result, the lack of internet connectivity caused multiple installation failure and prevented PIP from automatically resolving dependency conflicts. So this require our manual intervention. The next major challenge we faced was computational resource constraint. Fine-tuning large language model is highly time-consuming, with each training iteration takes several hours. We had to rely on Google Colab's paid subscription tiers to access the A100 GPU. However, this introduced another challenge, which is the risk of runtime timeout in Colab, which could result in the loss of all the progress being made during the training session. Through the testing, we determined that a safe training duration in Colab was within 4 to 5 hours. During the submission of the notebook for scoring, log and runtime feedback are not visible. This means that if the notebook threw an exception during evaluation, there was no direct way to trace the error source. To address this, custom logging utility was developed to print out process checkpoint and confirm which code section executed successfully before failure. To conclude, Gemma 2 with its larger parameter capacity demonstrates better performance over Delta V3 in capturing complex patterns, resulting in higher training accuracy and better leaderboard outcome. Despite limitations in computational resource and time, this project provides meaningful insight into large language model and motivate further work towards more efficient fine-tuning and accessible machine learning experiments. Yeah, this is end of presentation. Thank you.